Okay, so today's lecture will be basically, we'll focus on numbers conversion. So we already talked about the radix approach last lecture and how we can make different types of, or different conversions. And I mentioned that you need to be aware of some powers of 2, especially in the binary. Now let me discuss some examples here. Like 57 octal, convert this to decimal. How do we convert this? Using the radix representation. So you need to select the bits, which is first the radix here R, and here is or this is the base, or I'm sorry, then here R, which is here we have, I can call it N0, here it can be N1. So it will be N1 times R power 1 plus N0 times R power 0. Then you can substitute them, so it will be 5 times 8 power 1 plus 7 times 8 power 0. Then 5 times 8 is 40. 8 power 0, which is 1, times 7 will be 7. Then it will be 47 in hexa. Sometimes you don't need to write the first step. You can go directly and substitute them. But here I write it for your information so you can handle it. Another example. 1f as hexa. We need to convert this to decimal. So it will be 1 times 16 power 1 plus f times 16 power 0. So 1 times 16 power 1, which will be 16. 16 power 0 is what? 1. F times 16, f times 1, f. But remember, here we are in decimal, so the equivalent of f is 15. So 16 plus 15, this is 31. So. Clear? So in order to make any conversion, we can convert, you can use this radix representation, so we can convert, or this we call it the exponent representation. And when there's any decimal point, we already explained this last lecture. But sometimes this approach, especially you don't have a calculator, it might take so long. Especially how about if you have 17f16? How can you convert this? It will be like 1 times 16 power 2 plus 7 times 16 power 1 plus f times 16 power 0. But 16 power 2, it might be hard for you since, again, in this course there is no calculator allowed. And how about if it is 16 power 3 or 16 power 5? How can we deal with this? There is another way for making a simplification using the binary. How? We can convert any number to base 10, to base 2, or to binary, then we can make our conversion. So this is another way. So what I discussed before was valid, it was correct, valid everywhere. But now, how about if we can, how can we make it more convenient or more easier? Okay, so let's talk a little bit about the numbers. Octal, we know the digits from 0 to 7. So we can make the octal in a way that to make it converted to binary and vice versa, binary to octal and octal to binary, by making something we call it 3 bits representation. How? We can assume 0, 0, 0 as 0. Here is octal, here is binary, here is binary, here is octal. 0, 0, 0 as 0. While 0, 0, 1 as 1. 0, 0, 2, I'm sorry, it's not 2, we are binary. 0, 1, 0 as 2. 0, 1, 1 as 3. 1, 0, 0, 4, 101, 5, 110, 6, 1, 1, 1, 7. Okay? So as a result, we can use this to make it easier. So we can convert this from binary to octal and octal to binary easy. So let's look at for example, number 57. I need to convert this from octal to binary. So 5, look at the table, 101. So it will be 101. 7, look at the table, 111, 111. Then I can convert it easy. Okay? How can I convert this back from octal or from binary to octal? Group each 3 bits. Group this is equivalent to 7. Group this is equivalent to 5. Then this is an octal. Okay? So as a shortcut, we will realize that we can convert octal to binary and the vice versa using this table without, doing complicated calculations. So it will be easier. This table, most likely, it will be provided to you in either the quiz or in the exam. So you don't need to worry about memorizing this one. Or you can know how to handle it like the same way that I wrote it here. Then, in octal, we are grouping each 3 digits. Now, how about hexadecimal? We can group each 4 digits. Not 3. Now we will group each 4. Or something we call a nipple or half byte. We can group this. How do we do it? How can we do it? Which is basically, we have, for example, I think I already drew the table here. It's not here. Okay, I'm gonna draw it. I can write it on my own. It's based on 4. So here 0, 0, 0, 0. This is binary. 4 bits. Now here is in hexadecimal. I'm gonna make it a shortcut as hexa. So 0, 0 will be 0. Then 3 zeros 1, 1. 0, 0, 1, 0, 2. 0, 0, 11, 3. 0, 1, 0, 0, 4, 0, 1, 0, 1, 5, 0, 1, 1, 0, 6, 0, 1, 1, 1, 7, 1, 0, 0, 0, 8, 1, 0, 0, 1, 9, 1, 0, 1, 0. Now, we will not say 10 because in hexa we'll say A. Then 1, 0, 1, 1, B, 1, 1, 0, 0, C, 1, 1, 0, 1, D, 1, 1, 1, 0, E, 1, 1, 1, 1, F. So we have this table to make the conversion. Then the same way that we used to do it in octal, but in octal we used to convert each number to 3. Now we convert each number to 4 bits, and the vice versa. If we need to convert binary to octal, convert this, make this group each 4. So by looking at this example, like 31F, so the number 1F, look at 1, the representation of 1 is here. 0, 0, 0, 1. Here that was an octal. Now the representation of F, 1, 1, 1, 1. 1, 1, 1, 1. Then puts a number 2 here. So we can convert hexadecimal to binary easy. How about the opposites? Let me assume that we can have 1, 0, 0, 1, 1, 1, 1, 0. Now I need to convert this to hexa. This binary to hexa. How can I convert this binary to hexa? Group each 4 bits. So 1, 2, 3, 4. 1, 2, 3, 4. So 1, 0, 0, 1. Go to this table. 1, 0, 0, 1. Which is equivalent to number 9. And 1, 1, 1, 1, 0. Equivalent to E. Don't forget to write hexadecimal. Okay? Now, using the tables will make it much easier. So we can convert now any octal hexadecimal to binary and the vice versa easy. So we can go from octal to binary and the vice versa easy. Then hexadecimal to binary, the vice versa easy. So whenever, if you see any question, number in octal, convert this to hexadecimal, don't go directly from octal to hexadecimal. Go to binary first, then convert from binary to hexadecimal. So using this chart will make it easier. You have octal, find the decimal base. It's up to you. You can convert this to binary and convert binary to decimal, or you can use the radix representation that we used earlier. And the same here for the hexadecimal as well. It's up to you. Sometimes if it's too difficult to find the powers of 16 or the powers of 8, then convert this to binary. Then finding the power of 2 are much easier. Okay? And don't forget, when there is a radix point, then it should be something different, or which is, in other words, called a decimal point, and decimal point now is called radix point. Any questions? Okay, let's look at this question. Converts, or here, like we need to convert the numbers to binary. We didn't talk a lot how to convert the numbers to binary. Most likely we used to use the radix representation, or like as I said, showing the tables. But how can we convert 41 as decimal to binary? What you need to do is basically try to make it like this table. This is 41 divided by 2. So when you divide it by 2, it will be 20 and 1/2. What's the residue here? The residue is 1. Now, take this number. So 20 divided by 2, it will be 10. The residue is 0. So take this 0, put it this way. Then take this 10. 10 divided by 2 is 5. The residue is 0. 0 over 2. So take this 0. Then 5 divided by 2, it will be 2.5. 2.5. So take this 1. Then here, take the 0 here, take the 2 here. 2 divided by 2 will be 1, and the residue is 0. After that, 1 divided by 2, it will be 0, the residue is 1. Then start from the bottom to the top. Then put a brackets. Start with 1, 0, 1, 0, 0, 1. Then put number 2 here. So our main target is to reach to the 0. Once it's 0 over 2, then that's it. Stop here. Okay, clear? Now, can we validate this? Like, prove this is true. Use the radix representation. So here, this is bit 0, 1, 2, 3, 4, 5. So we can say 1 times 2 power 5 plus 4 times 2 power 0 plus 2 power 4 plus 1 times 2 power 3 plus 0 times 2 power 2 plus 1 times 2 power 0 plus, is this 1, 2, yes, 1, 2, 3, 4, 5, 6, 3, 4, 5, there's power 1 here, I'm sorry, I missed this part. 0 times 2 power 0, then 1 times 2 power 1, then times 2, 1 times 2 power 0. Okay? So it will be 2 power 5 plus 0 plus 2 power 3 plus 0 plus 0 plus 1 times 2 power 0, which will be 1. 2 power 3 is actually 8. So here is going to be, will be 8. This is 1. And 2 power 5 will be like here, you can see 8, 16, 32. 32 plus 8 will be 40 plus 1, 41. Now, is it 41? Yes. Yes.
So do you lay it out like backwards from your division? That makes sense?
Yeah, in the division, when I start this, then start, yeah, from the top to look at this arrow again. Okay? Then the same way it can be applied for the rests. So we can make this conversion back and forth. So, go back to the table. Now, we know how to convert decimal to binary and the vice versa. We know how to convert octal to binary and the vice versa, which is using the tables. We know how to convert hexadecimal to binary and the vice versa. Then using this chart, we can make any conversion easy in much easier way and very simple, very short time without taking so long. Okay, let's look at this example. We need to convert this number to binary or convert this to octal and to hexadecimal, or like different things. After converting this to binary, it will be like this one. So if I need to convert this to hexa, group each 4. Hexa, group each 4. So this is for 1110. It will be corresponding to E. Go to the table, 1110 corresponding to E. Then here, 0110, go to the table, 01110 equivalent to 6. Then 1001 equivalent to 9. Go to 1109. 1109, 01, I'm sorry, which is equivalent to 9. So that's how we do it. Just group each 4. How about convert this to octal? It will be group each 3. This 3 together, this 3 together, this 3 together, this 3 together. 100 equivalent to 4, 1015, 1015, 110 equivalent to 6. So we will realize that 2414 equals to 96E in hexa, which is equivalent to 4556 in octal, which is the same as 1001, 01101110 in decimal. In binary. So we realize they are all the same numbers. No, different representation, but they are all the same number, like different masks, while they are all the same person. Okay? Is this clear? Let's try some examples, more examples, so we can make sure everything is fine. 54, convert this to binary. Can you do it? Can please do it. Convert 54 to binary. Just keep dividing by 2 and take the residual. Then keep dividing until reaching to the 0. Okay. 54 divided by 2 is an even number, so it will be 27. The residue is 0. Then take this 27. 27 divided by 2, 13, 1 half. 13 divided by 2, 6, 1 half. 6 divided by 2, 3, the residue is 0. 3 divided by 2, which is 1, 1 half. 1 divided by 2, 0, 1 half. Then we're reaching 0, then stop here. try to collect the numbers. So, or cache numbers. So here we have 0, 1, 1, 0, 1, 1. But keep in mind, go like backwards, like start from the bottom to the top. Then it will be like 1, 1, 1, 1, 0, 1, 1, 0. Then this is binary. Now, can you convert this to octal? Group each 3. 1, 1, 0. Go to the table of the octal. Here is the table of the octal. 1, 1, 0, which is equivalent to 6. Then go back here. 1, 1, 0, 6. 1, 1, 0, 6. This is octal. 66 octal. Okay? The same number, can we convert this number to hexadecimal? Okay, let me rewrite the number here. 1, 1, 0, 1, 1, 0. This is binary. I need to convert this to hexa. The best way is to group each 4. Let's group them. Group them then. Here, let me use which this color. 1, 2, 3, 4. This is 1, 2. What will happen to the remaining 4? Yes? Zeros, right. Like assume them as zeros. So the first one, 0, 1, 1, 0. Go to the table. 0, 1, 1, 0 equivalent to 6. And the other parts, so this is equivalent to 6. 1, 1, 0, 0, 0, 1, 1. 0, 0, 1, 1, I think equivalent to 3. So you should be aware how to use the table. It will be equivalent to 3. 3. So as a result, it will be 36 hexadecimal. Okay? Any questions? Okay. Another example. Now we're trying to make it more complicated. How can we handle it? So here we have a radix points. We already discussed last lecture how to deal with this when there's a radix points. Basically, make sure when you make the conversion, you can count. This is as n0, this is n1, this is n negative 1, n negative 2, n negative 3. Then we can say convert this to decimal is going to be 1 times 2 power 1 plus 1 times 2 power 0. Now we are at the decimal point or at the radix point. Then plus 0 times 2 power negative 1 plus 1 times 2 power negative 2 plus 1 times 2 power negative 3. Okay? We already discussed this before. Now, how we find this? Here is will be 2 plus 0, 2 power 0, which is 1, plus 1, plus here is 0 times anything 0, plus 1 over 2, which is 1 over 4, plus 1 over 8, which is here will be 3 over 8, 1 over 8, then 2 plus 1, this will make it 3. So the answer I think will be 3. Now 3 over 8, how much will it be? 1 over 8, which is 1 over 4, 0.25. 1 over 8 will be 0.125. And here is 3. Then it's going to be 3.375. Is this right? 1 over 4, 0.25. 1 over 8, 0.125. Then 3. Yes, that's it. Clear? How about the opposites? We have 4.83. Convert this to binary. Oh, this is something new. How can we deal with this? This is the only case that I can isolate each one alone. How? Try to isolate 4. divided by 2, it will be 2, 0 over 2. Then 2 over 2, the residual is 0 as well. Then here 1 over 2 will be 0. The residual is 1. Then here is 0. Therefore, 4 alone is equivalent to starts from the bottom to the top. So it will be 1, 0, 0 binary. Right? You agree? Okay. Now, the challenge or the difference is in the next half, which is 0.83. Again, this is the only case that I can isolate each part. Otherwise, I cannot isolate it if I'm doing the opposite. So here, it's incorrect to say divided by 2. Don't use this. What should I do? Multiply by 2. Why we are multiplying, not dividing? Because remember that we have a negative here, negative when we calculate the index. So it looks like 0.83 times 2 power negative 1. That's how we are doing. Sorry, divided by 2 power negative 1. I apologize, let me do it again. It's divided by 2 power negative 1. So after the radix points, or like in the radix point in the right, divide by 2 power negative. In the left, divide by 2. So, and we know anything 1 over 2 power negative 1 is the same as 2 power 1, which is the same as when there is a negative power, just it will be multiplication instead of division. Therefore, it will be like this, 0.83 times 2. So it will be 1.66. Now, take the integer, take it off, or like you can circle around the integer, and take only the non-integer part here. So it will be here, the non-integer part, 0.66. Changing the colors sometimes mess me up. So 0.66 times 2, it will be 1.32. Now circle the integer and take only the non-integer parts. Then here, 0.32 times 2, it will be 0.64. No integer here, but no problem. Circle the 0. Then take the non-integer part here. So 0.64 times 2 equals to 1.28. Then circle the 1. And so on. We will keep doing this until reaching 0 with this part. Sometimes, some numbers like this number, it will take so long. I mean, it might take, maybe, I'm not sure if it's in infinite numbers or we'll keep doing this, but sometimes, if we have these kind of questions, you can stop by 3 or 4 bits, like by 4 bits, and that's it. So we already calculated 4 bits here because the residual is 0.28. We don't want to continue, keep going this. So then in this case, look at them and it will be, go this way, which is 1, 1, 0, 1. Go down. So we can say approximately this number will be, or we will say 0.83 approximately will be around 1101. Then, as a result, we can say 4.83 will be, take each number alone, .1101. This is in binary. Okay? Maybe when I choose 0.83, I was unfortunate choosing this number. Maybe if we choose different number like 0.75, it will be much easier. Okay? Any questions? So the overall idea, just not keep multiplying by 2, while the other one was dividing by 2. Let's look at more examples. Now, we have this number, and we need to convert this to octal. And we have a radix point. Keep in mind now we have a radix point. How to convert it? Using the tables. Here, we already have the tables here, so we can make the life easier. So how do we do it? Group each 3 in octal. But in order to group each 3, where should I start? Should I start from here? No, start from the radix point. Start from the left and from the right. So here is the radix points. Try to group each 3 here. Start from this point. So 1, 2, 3. And here, 1, 2. How about the third one, the missing parts? What should I do? Assume it's 0, right? Any missing parts, put it 0. Now, how about the other part? We have 1, 2, 3. Here we have 1, 2, 3. Here we have 1, 2. How about the missing parts? Make it 0. Okay? Now, you can try to compare this with the table. So the first number on the left, 0, 1, 1. 0, 1, 1, which is equivalent to number 3. Now, 0, 1, 0, equivalent to number 2. Now put a radix points. 1, 1, 0, 1, 1, 0, equivalent to number 6. 1, 1, 1, equivalent to number 7. 0, 1, don't forget this, 0. 0, 1, 0, 0, 1, 0, equivalent to 2. Then this is the number in octal. Okay? So you're just like doing more applications. How about convert this to hexadecimal? And instead of grouping each 3, group each 4. So then this example will be, you can try now, and let me know what's your answer. And keep in mind, there is the radix points, which is very important. Start from the radix point, start counting from that part. And group each 4. And here is the table, so you can look at it. So what's the number? Again?
Is it 19 like DD?
I got 1ADD. Okay. Let's think about it. So start from the radix points, 0, 1, 0, 1. Then here we have only 1. What should I put with the remaining 3? 0, 0, 0. Start from the lifts, 1, 1, 0, 1. 1, 1, 0, 1. So let's compare the first number in the lift. 0, 0, 0, 1, which is equivalent to 1. I think this may be confused some. How about 10, 10, 1, 0, 1, 0, 1, 0, 1, 0, equivalent to A. How about, don't forget the radix points. How about 1, 1, 0, 1, 1, 1, 0, 1, which is D. Then the other one is the same D. Then it's going to be 1A points DD. This is, and this in hexa. Sorry. Okay? Any questions? Now I'm gonna write another example that I think it can be very important in the quiz, which is we have 1f.2 16, which is hexa. Convert this to octal and decimal. How can we do it? You can convert this in decimal using the radix representation, but how about if I want to use, I would say I want to use the representation, the tables. So how can I convert this? Go back to the charts. We have the number in hexadecimal, or our number now in hexa. I need to find the octal. So go back to binary, then go back to octal. Or the other scenario, go to binary, then go to decimal. So let's do it. So 1 and f.2. How can I convert this to binary? Use the table. Each number will be in a group of 4. So 2, look at the table. Where is 2? Here is 2 in hexa, which is equivalent to 0, 0, 1, 0. So 0, 0, 1, 0. Then put a radix points. Okay? Then here is f. F equivalent to 1, 1. 4 ones. 1, 1, 1, 1. How about 1 here? Equivalent to 0, 0, 0, 1. 0, 0, 0, 1. Then this is in binary. Okay? Do you agree with me? Now, how can I convert this to octal? We need to convert it to octal. Remember, octal group each 3. Start from the radix points. So here's 1, 2, 3. 1, 2, 3. Here is 1, 2, the leading, there is the missing part, which is 0. Then here is the radix points. Here is 1, 2, 3. Then here is 0, the missing parts are zeros. So we can say that 0, 0, 0 is equivalent to 0. 0, 1, 1. Go to the table. 0, 1, 1 equivalent to 3. Then here we have 1, 1, 1 equivalent to 7. Put the radix points. 0, 0, 0, 0, 0, 1 equivalent to 1. Then 0, 0, 0 equivalent to 0. Therefore, this number can be presented in octal as 037.10 octal. Sometimes, as a shortcut, the zeros in the left and zeros in the right does not make sense. So we can say as 37.1 octal. Then these both are the same. Okay? Now, how can we convert this to hexa to decimal? The other option, which is you already found it to octal. How to find it to decimal? You have 2 options. The first option, convert this to decimal. Okay, let me choose different colors. You can convert this to decimal. And if you think this will take a lot of time, what's the easiest way? You can say 1.2f, convert this to decimal, which is basically 1 times 16 power 1 plus f times 16 power 0 plus 2 times 16 power negative 1. Don't forget this. This number, since it have only 16 power 1, 16 power negative 1, it can be easy to do it in this way, radix representation. But if it is more than that, like 16 power negative 2 might take so long, 16 power 2 might take so long. If you can do it, it's fine. If you feel nuts, then you can go to the representation, binary, convert binary to octal. So it will be like 16 plus 16 times 0, which will be 1 times f plus 15, plus here 2 over 16, which is 1 over 8. Then it's going to be 31.1 over 8, 0.125. Let me see. 31 plus 0.125. Yeah. Then it's going to be 31.125. This is in this. Okay? Any questions? Okay. In summary, for any base R, we can use the radix representation. So we can, no matter if it's octal, hexadecimal, if someone create his own system like 10 bits or 10 digits or 15, 17 digits, like you need to make sure that how to create the symbols for each number. But you can build your own system using the radix representation, then it can be done. But here in this course, we focus on binary, which has only 2 digits, which is 0 or 1. So an octal, which is 8 digits, then it can be from 0, 1 until 7. Hexadecimal, which is 16 symbols, so we are from 0, 1 until F. Then we have the decimal that we used to deal with it, which is from 0 to 9. Base 10 from 0 to 9. Okay? Most likely, the conversion, we already know how to do it. In powers of 2, we already discussed this last lecture. So the kilo in binary, or like in the computers, is not like 1000, it's 1024. So the same, I think many of you are familiar, like the gigabyte is 1024. Megabyte and terabyte, 1024 gigabyte, and so on. So it's not exactly 1000, there's 1024, and the main reason because 2 power 10 equals to 1024. This is the main reason for this. Then in computer systems, all of these are based on these scenarios. Now, let's go to something we call arithmetic analysis, which is we need to make addition, subtraction, multiplication, and division using, in this course, I'm going to focus only on binary and decimal. So starting from now, for dealing with the numbers, I will not talk a lot about the hexadecimal. I will not talk a lot about octal. Because any decimal or octal, using the tables, can be as binary, right? We can convert any number to binary, as shown here. So, if we know how to deal with binary and make our programs to dealing with binary, then we can deal with decimal, or we can deal with hexadecimal, we can deal with octal at any time. So to avoid confusion and overcomplication, let's know how to deal with the binary. So how to deal with binary and decimal. Arithmetic analysis, as we know, in addition, multiplication, subtraction, and division. And there's something about like signed numbers, which is the negative numbers, how can be this represented. Because all of these numbers that we talked about, the rational numbers after the decimal point or the radix points, and we talked about how to deal with different types. But how about if these numbers will be negative? How can we represent them? Let's first talk about the arithmetics, addition, multiplication, subtraction, and division. Then we will go to we call it signed numbers or the negative numbers. Binary addition. How to make the addition? Again, we will focus here in binary. Like, we know in any addition, from school, 19, for example, plus 11, this is in decimal. 9 plus 1, 10, which is 0, carry 1. 1 plus 1, 2, plus 1, 3, 30. Yes? That's so straightforward. But here, 1 plus 1, 2. But there is no 2 here. What's the next number after 1? It's 10. Again, how we can calculate 0, 1, 10, 100, 11, 100, right? That's how we calculate the binary. So the scenarios that we can have 0 plus 0, which is 0. 0 plus 1, which will be what? 1. 1 plus 0 equals to 1. 1 plus 1 equals to what? 11. Or 1 carry 1, which is 11. Okay? These are the scenarios that we can have some possibilities. We can have some scenario like 1 plus 1 plus 1. 1 plus 1, 10. I'm sorry, 10, not 11, I apologize. And the past here. 1 plus 1 is 10. Now here, 1 plus 1, 10. Plus 1, 11. So these are like one of the mathematical or programmable joke. 1 plus 1, 10. 1 plus 1 plus 1, 11. Okay. 1, let's go here. Start in this part. 1 plus 1, 10. So 0, carry 1. 1 plus 0, 1. Plus 1, 10. 0, carry 1. 1 plus 1, 10. Plus 1, 11. 1, carry 1. Right? 1 plus 1, 10. Plus 0, 10. So 0, carry 1. 1 plus 1, 10. Plus 1, 11. 1, carry 1. 1 plus 1, 10. Like this. Okay? So here we will see that we have a carry bits. Right? We have some carry bits when we deal with these numbers. So you need just to keep this in mind and take this into consideration. How about assuming that I need to calculate this, or you can try it by now. 101 plus 111. How much will be? One plus 1, 10, 0 carry 1. 1 plus 0 plus 1, 10, 0 carry 1. 1 plus 1 plus 1, 11. Right? That's it. Let's talk about the subtraction. How the subtraction behavior will be. The same as the normal subtraction when we need to take two borrows from the other digits, so the same way. Let me choose a small example, then we can go to the other one. So I need to subtract 111 from 101. How can we subtract this? 1 minus 1, 0. 1 minus 0, 1. 1 minus 1, 0. Or in summary, we can say it's 10. Here, I don't need to take to borrow because it's straightforward, right? How about this scenario? 1 minus 1, 0. 0 minus 1. We cannot. What should I do? You need to borrow. Let's borrow this one. So this will be 0. And this one will be 10. 10 minus 1, 1. Because 1 plus 1 equals 10. Now, we have 0 and the other digits. 0 minus 1, oh, we cannot, it will be 0. I'm sorry, 0 minus 1. Still, this is not right. So we need to borrow. This will be 0, this will be 10. 10 minus 1 will be 1, because 1 plus 1 equals to 10. Then here, 0 minus 0, 0. 1 minus 1, 0. Then this one remains. Okay? Does this make sense? Okay, so you just need to be careful to be aware how to deal with this kind of addition, subtraction, multiplication, and division. Let's look at multiplications. In multiplication, keep in mind like these scenarios. 1 times 1 equals to 1. 1 times 0 equals to 0. 0 times 1 equals to 0. 0 times 0 equals to 0. Okay? Then we can do the multiplication the same as we used to do it back in school. When you do the multiplication, start with the first one and do the multiplication. Then the second one, do multiplication, and so on. Let's start with the first one. 0 times anything will be zeros. So it will be even like easier, 0. This 0 times 1, 0. 0 times 0, 0. 0 times 1, 0. 0 times 1, 0. 0 times 1, 0. 0 times 1, 0. So they are all zeros. Sometimes you don't need to make the multiplication, just put zeros. Now, when you go to the next digit, keep in mind, start counting from the following digit, and so on. So, 1 times all of this will be the same as this number. So it will be here 1, 0, 1, 1, 1, 1. Again, keep in mind, don't forget to shift these bits. This is from mathematics, from school. Then, here is 0. So put zeros. 0, 0, 0, 0, 0, 0. Then here 1, put the same number, but don't forget to shift the numbers. So here is 1, 0, 1, 1, 1, 1. Now you can make the addition. So keep in mind, like this will go this way, will go this way, will go this way. 0, there is nothing to add, here is 0. 0 plus 1, 1. 0 plus 0 plus 0, 0. 0 plus 1, 1 plus 0, 0. Plus 1, 10. 0, carry 1. 1 plus 0, 1 plus 1, 10. Plus 0, 10 plus 0, 10. So still 0, carry 1. 1 plus 0, 1 plus 1, 10 plus 0, 10 plus 1, 11. 1, carry 1. 1 plus 1, 10 plus 0, still 10 plus 1, 11. 1, carry 1. Let me put the carry. I don't want. I'm going to change the color so we don't want to get confused between the carry and the digits. So I'm sorry, let me do it again. Here is 0, here is 1, here is 0, then here is 10, then here is 10, here is 11, here is 11, here is 10, then here is 10. So as a result, let me write it like 1, 0, 0, 1, 1, 0, 0, 1, 0. Okay? Understood?
Sorry.
Yes.
What's that? Is that a 0?
Yes.
Okay. 3 zeros? Okay.
Yeah, I rewrite it here, so. Now, how about the division? You know from back school, the log division. So we need to apply the log division. How we make this division? Let me rewrite this number here. We need to divide 1, 0, 0, 1, 0, 1, 1, divide by 11. How much will it be? Using the log division, here is 11, here is 1, 0, 0, 1, 0, 1, 1. Now, starts with the first bit here. 1 divided by 11, no integer, so it will be 0 here. I'm sorry. Will be 0. Then 0 times 11 will be 0. So subtract 0. This will be go down. Then it will be 10. 10 divided by 11. Still no integer. No more than 11. So 10 still below than 11. Then it will be 0. 0 times 11. Here will be 0. Then all of this will be like 100. 100 divided by 11. 100 is more than 11. Then put 1. 1 times 11, 11. Subtracts. 100 minus 11 is what? 1. Because, 100 minus 11 is 1. In binary. Remember, we are in binary. Then, put this one. 11 divided by 11, 1. Subtract 11. So the answer will be 0 here. Then, this 0 will be down. 0 divided by 11, still 0 because we cannot subtract this, so minus 0. Then this one will be here. 1 divided by 11, 0. Then subtract the 0 here. So this 11 will fall down. So it will be 11. 11 divided by 11, 1. Then subtract 11. Then no more numbers. So as a result, it will be 0, 0, 1, 1, 0, 1. 0, 0, 1, 1, 0, 0, 1. So to write the final answer, the leading zeros are not necessarily, so it can be 1, 1, 0, 0, 1. Okay? All of them are in binary, of course. If we need to deal with hexadecimal octal, this will not be included in this course. It will be too complicated, but most likely, how's the computer dealing with it? Convert this to binary, and when everything is binary, it will be fine. Any questions? So now you all should be aware how to do the arithmetic analysis, finding the addition, subtraction, multiplication, division. You should be aware how to make the conversion between binary, hexadecimal, decimal, octal, between all of these. Again, because it will be included in the Friday's quiz. And also, you need to know how to make the, to convert when there is a radix point or when there is decimal points. How about the signed integers? This is something that's make it more complicated in the binary systems. The positive numbers, or the numbers that we discussed earlier, they're all positive, so it was fine. We can represent this. But whenever there's a signed number, it creates a problem. What's this problem? This problem comes because when there's a negative sign, what should I do? There was one approach. We need to add a bits. It's called signed bits. So let's assume we have 4-bit system. Then we can add 1 bit as sign. So the total will be 5 bits. So starting from now, maybe we will discuss about the systems, 4 bits, 6 bits, 8 bits, or 4 bits, 8 bits, and so on. So these bits, depending on the capacity of the microprocessor. So sometimes the microprocessor or the device that you have, it has its own number of bits capacity. Remember or recall the computers. You have a 32 bits, 64 bits, old computers, some of them were 8 bits, 4 bits. So these computers, based on like each character will be as 4 bits, as a register 4 bits. It cannot go more than that. So let's assume that we have this device that can capable of handling only 4 bits. Then we add a bits number 5 to represent the sign. So that sign bits, if it is 0, this will make it positive number. If it is 1, this will make it negative number. So we can clearly say that the first bit is only associated with the sign, while the remaining bits are the numbers. So you need to be aware when we deal with the signed numbers that how many bits or what's the register that I have can handle. It can handle 4 bits, then I can say that the one in the left will be, we call it the signed bits. So here is an example. 1101. 1101, or this is 01101. Let's take the first 4 for the numbers, and this is for the digit, for the sign. So it's going to be positive because of the 0. And 1101, when you convert this to binary, it will be 13. So it will be positive 13. On the other hand, look at the other number, 1101, and here is bit 1. So the sign is negative. 1101, this corresponds to 13, so it will be negative 13. 0000, so here is positive, and here is 0000, this is equivalent to 0, positive 0. How about this? 1000, so this is negative, and 00000. So we realize there's something weird. Is there really a positive 0 or negative 0? No, 0 is neutral. But we would realize that the 0 has two representations. The 0 can be represented as 0, 0, 0, 0, or it can be as 1, 0, 0, 0, 0. We have two representations of 0. And this representations is called signed magnitude representations. You need to be aware of the definition of this one, because there will be another representation we will discuss also in this course. So the signed representation, the disadvantage of this one, we have two representations of 0. And basically this representation based on, look at the first bit on the left. If it is 0, then it's positive number. If it is 1, then it's negative number. I think this is the table that summarizes the 5 bits register as shown here. So we have two representations of 0. We have positive 0 and negative 0, while in the real life they are all zeros. And we can see the positive numbers are the same numbers that we used to know earlier, how to deal with it. The negative numbers, just put 1. Between negative 1 and 1, replace this sign. Between 2, positive 2, and negative 2, just this 1. And so on. Right? Then, in this scenario, or when you deal with the call it signed representation magnitude or signed magnitude representations for the negative numbers in binary, just take a look at the signed bit, or take a look at the first bit on the left, which we call it the most significant bit. Look at it. And this one will be associated with the signs, while the rest, keep in mind, will be associated with the number. Then this representation, yes, can pass in representing the negative number, but it has some flaws. One of the flaws, two representations of 0. And actually there are other flaws. Like what? Let's assume we need to make this addition. Like 9 plus 2. 9 plus 2, as we know, is 11, right? How about we make this in binary? So here we have 1 plus 0, 1. 0 plus 1, 1. 0 plus 0, 0. 1 plus 0, 1. Then here remaining 0. 0, 1, 0, 1, 1. So how can we convert this to make sure if our answer is correct? This is in binary 2. We can convert this to decimal, which is by mentioning this is 0, 1, 2, 3, 4. So it will be 0 times 2 power 4 plus 1 times 2 power 3 plus 0 times 2 power 2 again plus 0 times 2 power 2 plus 1 times 2 power 1 plus 1 times 2 power 0. So we will end up, we have 8, because here this is 0, here is 8, this is 0, this is 2, this is 1. So which will be 11. Then our answer is correct. This representation can pass. But the flaws of this, when we will deal with negative numbers, how can we deal with this? Let's imagine we need to say 9 minus 2. How can we deal with this subtraction? We can say it will be 9 plus negative 2. So it can be easier. How to deal with 9 plus negative 2? As we know, 9 plus negative 2, this will be 7. How to deal with this here? Go to the 2 representation, which will be 0, 0, 1, 0, and add 1 because it's negative number. Right? Now let's do the addition. So by doing the addition, 1 plus 0, 1. 0 plus 1, 1. 0 plus 0, 0. 1 plus 0, 1. 0 plus 1, 1. Okay. Let's look at this number. This number says that the first digit says it's negative. Is this true? 9 minus 2, 7. But using this representation, when we add, make the subtraction, we will realize that the number is negative. By converting this number, 1 here, this means it's negative, and this number, convert this to binary, to hexadecimal, it will be 11. Do you think the answer is negative 11? No, it's 7. So this representation fails. Signed magnetic representation fails in case of addition between negative number or subtraction, or addition between negative number and positive number. When we combine between both, it will be problem. So this signed magnitude fails on this one. This is another flow. So we need to look for another representation that can handle or can deal with these problems. Okay? Here I'm showing you like step by step. So that's how our first approach. We realize, okay, we can represent the negative numbers. Okay, that's perfect. Then there's a flows. The zeros has two representation. Okay, no problem, whatever. That can be fine. But when we add the addition, it works. Okay, that's fine. But when we make addition and subtraction, or between positive and negative number, this will create a problem. This will create false results, which is not right. Therefore, this can turn addition into subtraction, or can make the negative numbers as positive, or the positive as negative. So, again, the flaws of this, two representations of 0, and different cases in addition and subtraction creates a lot of problems. Okay? So this representation, based on, we call it 3 bits, plus 1 bit for sign. Again, this is different than this part. This part I discussed, we call it 5 bits, which is 4 bits plus 1 sign. Now, it depends on the register, again, depending on the manufacturer. So it can be, for example, this is representation based on 3 bits. Okay? So whatever, just like, make sure if it is 3 bits or 4 bits in sign magnitude, one of them reserved for the sign, the rest for the number. Okay? Any sign magnitude, there is only one for the sign, then the remaining, whatever, how many, if it is 3 bits, 4 bits, 5 bits, 8 bits, 16 bits, and etc. Just keep in mind the first one is located for the sign. Now, using the 3 bits magnitude, can we find any representation that makes the life easier? Yes. There's something we call it complements. Complements can make the life easier. So, as we know, like 1 plus 1 equals 2, positive plus negative equal to 0. Let me say positive 1 plus negative 1 equals to 0, right? Or positive A plus negative A. Bad intro, I'm sorry. Plus negative A will be 0. So we can replace negative A by complements. Like we can say A plus A bar, right? So in other words, I mean, let's forget about the way, which is, I'm going to draw it in a different way. Apologize. Positive plus negative. This will complete each other, will be complements. Okay? Let's look at a cup. We have the first filled half of the cup, and we have the empty half, right? So sometimes they used to say, look at the filled half of the cup to be more optimistic. So what's the complements in order to make the cup completed? Which is the second half, right? So the second half is called the complements. So the complements basically are the opposite, or the other half, or the missed part of it, which is the other half of the cup. Then the complements sometimes can be used as indication of the negative. So we can say this cup with the full cup plus the remaining unhalved will make it a full cup. Right? So we can say this cup, I'm going to denote it by A. The unfilled part, I'm going to call it A bar, will be a full, which is I'm going to call it 1. Therefore, the complement A bar will be 1 minus A. This is the complement. This thing we call as a complement. So, the complements will be we can use it to represent the negative number. It's depending also on the base. So, we have two types of complements. We have the radix complements based on tens or based on decimals and based on binary. And we have something we call it diminished radix complement, which is r minus 1 complement, or in other words, we can deal with the decimals or nines complements or ones complements. Basically, in decimal, base 10, and in binary, base 2, right? So in decimal, when we do it in decimal, we will call it 2 tens complements. When we do it in binary, we'll call it 2's complements. However, there is another complement, it's called diminished radix complement. So we can say 10 minus 1, which is 9's complements, and we have 2 minus 1, which is 1's complements. Why we have these scenarios? I'm going to go through it now. But these two, or these bases, exist because we need to make sure, I think we're running out of time, so we have 1 minute. So we need to make sure that if we make the complement first, can the complement achieve the negative number? That's what we will expect to see next lecture. How to apply first, we call it diminished radix complement, which is the 9's complement and 1's complement. After that, we will go to 2's complement and 10's complements. So next lecture, we will realize that we will reach only a representation such that there's unique representation for 0, and there will be no problem with the addition and subtraction as we see it before. So that's we will see it next lecture. Thank you so much. See you next lecture.